Hello everyone, this is the last section of our review of the 2022 AMC10A paper. So most likely what I'll be doing is I'll be reviewing the AMC12B next, so in order to sort of offset between the AMC10 and 12 because there's overlaps, so going through the AMC12A would be a little bit weird since there's about a 50% overlap with the AMC10A. Before we get to the questions, just a little bit of a PSA, which is that for the AMC, if you would like to register through our center, the deadline for registration is the 17th of October. That's mostly determined by the MAA and not by us. So it's the 17th of October, and this is of course quite a distance away from the actual dates, so just take note, as well as take note of the timings. The timings are not standardized for every place you take it, so if you're doing it in school, just make sure that you know the timing you're taking it in school, right? The timing depends on the individual centers, but of course the guideline is that no one can share the questions for I think 24 to 48 hours, so if you're taking it earlier or later, just don't share the questions and it will be fair. Right, and of course the natural guidelines are that the AMC 10 you must be below grade 10, and for AMC 12 you have to be below grade 12. Quick advertisement. This is not a sponsored video, this is just self-advertising, which is that the classes are from the 23rd to 27th or the 31st to 4th of November. So that's between the closing of the registration as well as the actual AMC dates on the 9th and 15th November. So if you are keen to join, this is just the schedule, which is a screen grab from the form, which you can still find in the description below. Alright, so now let's start looking at our problems. So for this video, as you have seen on the thumbnail, I have mentioned that there is this dynamic practical solutions versus rigorous proofs. Now this is important because if you are trying to do the last few problems, they are all going to be, or rather they are usually going to be difficult to solve properly. But some of them have so-called clever shortcuts. I recorded a video some time ago about how to guess answers, and the AMC is multiple choice, so that's one thing that could happen. It is possible to guess answers for some of these problems. And then there are those where it is simply not possible at all. We're going to look at these 6 problems, and hopefully it gives you also a sense of when you can guess and when you have no choice but to follow the intended approach. So let's begin with question 20. A 4-term sequence is formed by adding each term of a 4-term arithmetic sequence to the corresponding term of a 4-term geometric sequence. So arithmetic sequence means common difference. I can just let the terms be A plus D, A plus 2D, A plus 3D. Geometric sequence means a common ratio that you keep multiplying, so I will use a different letter B and R for ratio. And apparently the sums are 57, 60, 91, and you are supposed to find the 4th one. So let's just write down the equations first. Right? A plus B equals 57, A plus D plus BR equals 60, A plus 2D plus BR squared equals to 91. What can we do here? Now the first thing I want to do is just to eliminate A. Right? That looks very tempting, so subtraction. And subtraction again. Okay, so now I'm left with 3 unknowns and 2 equations. Now that would normally be not enough, but we have to recall that the question says positive integers. important note is that it means that the terms are positive integers, so a and b have to be positive integers, r and d might not. They may not need to be positive. Okay, d does not need to be positive, r does not need to be an integer. Now with that in mind, I know that as long as I bring it down to enough variables, I can probably guess and check. So I'm going to just subtract one more time to eliminate d. And factorize. Now what I just said is that I don't know that r is an integer. But what I do know is that b is an integer and r is still at least rational. Right? It could be, let's say the sequence goes 200, 150 and 25, so r is half. Something like that could happen, but if r is irrational, of course that would not work. Which means that I could just try some reasonable possibilities of b and see whether it works. This is the AMC style, right? You don't need to prove things. So we just try b equals to 7, because that would allow what's left over to be squared. So I try b equals to 7, and that would mean that r minus 1 squared is 4, r minus 1 is 2, and r equals to 3. So let's check. If b is 7 and r is 3, this goes 7, 21, 63. That would force the sequence to go 50, 39, 28, and lo and behold, it is an arithmetic sequence, minus 11, and so it would give me 17 down here and 189, which means that this is equal to 206. Now if you wanted to prove this, you would definitely need to go through some extra hoops, like okay, check b equals to 28. What if r minus 1 squared is less than 1? Will anything go wrong? Don't do that for AMC. You have not enough time. Make these kinds of reasonable guesses and you're more likely to succeed than not. Speaking of reasonable guesses, question 21 is a perfect example of you would like to make a reasonable guess. There are a couple of ways in which you could actually do this question properly. One way would be to use vectors. Another way would be to use some coordinates. Another way would be to know that this is actually half of a truncated octahedron, which is a solid that if you just Google it, it refers to a specific shape with these specific faces, and you will be able to therefore learn a bunch of properties. It basically consists of some hexagons and some squares. If you don't want to do any of this, you can make some reasonable assumptions using one very simple heuristic. Is the diagram rather to scale? Now, of course, this is three-dimensional. There's no such thing as a scale diagram per se, but does it look reasonable? And the answer is yes. These do look like regular hexagons, and it does look like you have a square below, and it does look like you have got the edges of your hexagons coinciding. So all of this looks believable. All the side lengths are 1 at the bottom. All the side lengths here at the top are also 1, just as believable. So the only thing we need to know would be what are the other 4 lengths. Now, what I'm going to claim is that if we knew that this is half of a truncated octahedron, or if we just looked at it visually, it does seem like this is 90 degrees. It's also very believable it's 90 degrees because this thing is symmetric. That's technically not a proof, but you can verify it, and I'm just going to leave it as that. So these will all be square root 2, if that were true, which it is. And because of symmetry again, this is actually equiangular. It is all going to be 135 degrees. And so if it's equiangular, it means that by extending it out, you would get a square. And not just any square, it would be a square of side length 3. So the area of this octagon would be 3 squared minus each of these triangles is 1/2. We get 7. Now I think we can stick with that. Once again, there are ways to verify this, most likely not within the duration of an AMC. Question 22. Suppose that 13 cards numbered 1 to 13 are arranged in a row. The task is to pick them up in numerically increasing order, working repeatedly from left to right. For example, 1, 2, and 3 are picked up on the first pass. Then you restart, you get 4 and 5. 6 is on the left, so you go again. 7 is on the left further, so you go again. 8, 9, 10, and then finally 11, 12, 13. So 5 passes. For how many of the 13 factorial possible orderings of the cards will the 13 cards be picked up in exactly 2 passes? Okay. The trick to this question, again, if we are being practical, would be that I can see the options here and one of them stands out to me. This is 2 to the power of 12. I can see that all the options revolve around this. This is 2 to the 12 minus 1. This is 2 to the 12 minus 14, which is conceivably related to the 13 cards. This is 2 to the 13 minus 14. And this is 2 to the 13 minus 1. 2 to the 13 is twice of 4096, which is 8192. Now, all of these look like they are making a general claim, right? If 13 cards, if I were to let this thing be n, excuse me, it's as if this is 2 to the n minus 1 minus n plus 1. This is 2 to the n minus 1 minus 1. This is the 2 to the n minus 1. This is 2 to the n minus n plus 1. And this is 2 to the n minus 1. So it looks as if you are claiming this. Now, we can actually test this out on a smaller case. So I'm going to test this out on just fewer cards. Of course, if there is one card, that is impossible. If there's 2 cards, there's one way. Right? You've got 1 to the right of 2. Now, at this point, you don't want to settle on this yet because usually the smallest cases might be exceptions. So I don't trust this. I want to at least get 3 and then maybe 4. So for 3, I can just list. Right? So 1, 2, 3 is 1 pass. 1, 3, 2 will be fine. 2, 1, 3 is also 2 passes. 2, 3, 1 is also 2 passes. 3, 1, 2 also, and 3, 2, 1 no. So this would be 4 ways. Technically, at this point, if you were to check all of these options, you would already find that the only one that is consistent with n equals to 1, 2, and 3 is this. I would probably take that in a competition. Once more, I will leave the so-called proper idea for you to think about. But a hint is that because you are essentially taking 2 passes, this has something to do with just labeling all of the numbers 1 and 2. So it is something like 2 to the power of 13, but not exactly, because there are some exceptions. For instance, you can't have all 1s, you can't have all 2s, and you cannot have a bunch of 1s followed by a bunch of 2s. It's not too hard to verify from that, but this is what I would do in the AMC. Okay, so you have seen 3 questions now where we have not quite done a rigorous solution. We have not made a random guess, but we are making very highly educated guesses. We then get to question 23 where can't really guess if I don't draw something first, right? I need to see what's going on. So let's draw it. For a geometry question, don't start drawing until you have just looked at the problem and seen what's the most important kind of feature that you want to preserve. So this is an isosceles trapezoid, or trapezium, where BC is less than AD. And if you look at the options, I have no idea how much shorter it is than AD. So let's just give this a try. Something like this should look symmetric. Now PA equals to 1, PB equals to 2, PC equals to 3, PD equals to 4. Let's try something like P somewhere here. Right, it's not perfect, but it actually looks somewhat reasonable. Somewhat reasonable is all that we need for computational problems like that. I say computational because it's not one of those where we expect to do angle chasing and notice a surprise parallel line. These are pretty much exactly what you think they are. Okay, so now that I have gotten this stuff down, I am going to look at it and quickly decide that I don't have any similar triangles. I also don't really know how to guess from the very start. I can't make any assumptions, because the assumption that I want normally would be that it's symmetric, and it already is symmetric. Now, some of you may actually remember that there is this property for rectangles that says that a squared plus b squared would be equal to c squared plus d squared. And this is just from Pythagoras. It's I think known as the British flag theorem. So I'm going to take some inspiration, and the inspiration I'm going to take is that I can also drop a bunch of perpendiculars all over the place. Well, not as many perpendiculars perhaps, because this is an isosceles trapezium, but I am just going to draw it down here. The same line will be perpendicular to both sides. I'm just going to call this H1 and H2, and I'm just going to call these 4 lengths A, B, C, D. Pro tip, don't write down the square roots. Write down all the equations from Pythagoras. It often works better. So just write down a squared plus h2 squared equals to 1 squared. B squared plus h1 squared equals to 2 squared. C squared plus h1 squared equals to 3 squared. And D squared plus h2 squared equals to 4 squared. What else do we know? That often is related to what else have we not used, and in this case we have not yet used the isosceles information. Now, the fact that it is symmetric would mean that if I were to chop this up like that, D minus C and A minus B are equal. So that's one bonus equation that comes out from the isosceles condition. And what do I want? What I want is BC over AD, which is B plus C over A plus D. Okay, so with that in mind, I realize that I don't care about H1 and H2. So I'm going to eliminate them by subtraction. So this gives me D squared minus A squared equals to 15. And I see, hang on a moment, this is actually quite related to what I'm supposed to find. Because B and C and A and D are also joined together. So if I were to just divide, this is 1/3. And I can factor out the B plus C and the A plus D. And I guess the last thing that we have not used now comes into play. This actually tells you that C minus B and D minus A are equal. And so your answer is just 1/3. To be honest, this is not very hard if you have, like, let's say 10 minutes of time. If you have that 10 minutes of time, you can easily do this. But if you do not have that 10 minutes of time, this is a question that is less conducive to our guesstimation than the previous problems. Now, moving to question 24, we are back in business with our guesstimations again. Now, before we even read the question, I look at the options and I say, oh, this is very juicy. This is juicy because I see nice numbers. 625 is 5 to the power of 4. 1296 is 36 squared, is 6 to the power of 4. And maybe you also will see some other nice features, like I'm not sure what's 500, I'm not sure what's 1199. 1089 is 33 squared. I don't know why it would be 33 squared, but these are nice numbers. And since these are nice numbers, it suggests that there might be a pattern again. Now let's read the question, because this is quite a mouthful. How many strings of length 5 from the digits 0, 1, 2, 3 and 4 are there, such that for each j from 1 to 4, at least j of the digits are less than j? Okay, and helpfully the question sort of expands this out in words. What are the 4 things that it says? At least 1 digit less than 1. Well, that means that you have at least 1 0, right? Because that's the only digit less than 1. And then the next one, at least 2 digits less than 2 means at least 2 zeros and 1s. And I guess let's put that all down. Now, at least 1 0 is quite easy to interpret. I guess at least 4 of 0, 1, 2, 3 and 4, 0, 1, 2 and 3, but 4 excluded, means that you have at most 1 4. And this one you could say at most 2 of your 3 and 4. Now I'm going to show you 2 ways in which you can guess the answer, or rather you can know that you have a correct answer without really solving the question in full again. The first way is, again, to find a pattern. Now, if I ask how many strings of length 1 with only 0, there will just be 1. I can't tell anything from that. Now length 2, meaning that I've got zeros and ones. I can say that I need at least 1 0 is the only rule that I need to worry about. So at least 1 0 means that not 1 1. So 0 0 is okay, 0 1 is okay, 1 0 is okay, and so this would be 3. I cannot find a pattern from 1 3, so I should at least do one more. Now for counting length 3, I think I can do complementary counting because there are only 2 conditions. Means that I need to exclude those cases that don't have at least 1 0. Don't have at least 1 0 means that no zeros. And exclude those that don't have at least 2 of 0 and 1. That will only happen if you have at least 2 2s. So I can just say that no zeros, there are 2 cubed of them, right? 1 or 2 in each place. And at least 2 2s, the only ones that I haven't already subtracted off are those which have got a 0 inside. So 3 more that I didn't subtract. So 3 cubed minus 2 cubed minus 3, this is equal to 16. That is actually quite special. Now let's see what all of these are, because at least 3 of these options look like powers. So 3 can only be 3 to the power of 1. (16) could be 2 to the 4 and 4 to the power of 2. But if we were to look at a pattern, this is more likely to be consistent because 1 is also 2 to the power of 0. So it is consistent for pattern. And if this is the pattern, then length 5 should most likely give you 6 to the power of 4. That's consistent. Once again, before we move on, I want to say the alternative, but the alternative here is there's another rather humorous trick which was discovered by some participants last year, which is that the rules do not control the arrangement. The rules only control combinations. So if some combination works, so all its permutations work. For instance, in the example, if it says 0, 2, 2, 1, 4 satisfies the condition, it means that all the permutations of 0, 2, 2, 1, 4 will satisfy the condition, right? So 0, 2, 2, 1, 4 would be giving you 60 permutations. Now the trick was actually quite funny, which is that you would realize that if there are 5 items, the permutations would be 5 factorial over some factorials depending on the repetition. But this will always be a multiple of 5. Except if it's 5 factorial over 5 factorial. Meaning that it's just the same number repeated 5 times, and that would be 0, 0, 0, 0, 0, which has 1 way to be permuted. So you're going to get your answer must be 1 mod 5. Which will also point you to 1296 because coincidentally none of the other options are 1 mod 5. Now the intended solution is a rather clever but hard to think of bijection. Feel free to think about it to see what kind of bijection will give you these powers. But I think both of these are much more likely things to think about if you're giving yourself about a 5 to 7 minute time frame. Finally, we get to a question where there is no escape from lots of solving. And I'll be honest, right? I recorded this section, and when I tried to record this section for the last question, the algebra got a bit messy, I made a mistake, and so now I am redoing it again. It is not possible to get around this. So what you should think about this is just a warning. The solution to this question is essentially a warning. It's a warning that AMC questions can take this long, and so you have to be really fast before you think of, let's say, I want to try every question. Or even more ambitiously, if you want to get a perfect score. You have to be able to finish, let's say, 20 questions in about 40 minutes if you want to even think of getting a perfect score, because whichever 5 questions you have left for yourself, you easily need 30 minutes. Okay, so now with that said, let's still go through this anyway. It's not impossible, it just takes quite a while. So let R, S, and T be squares that have vertices at lattice points whose coordinates are both integers. In the coordinate plane together with the interiors, the bottom edge of each square is on the x-axis, I can see that. The left edge of R and the right edge of S on the y-axis, I can see that. And R contains 9/4 as many lattice points as does S. Okay, so I think I know what to do first, because this means that I have got a ratio. R contains 9/4 as many lattice points as does S, so I'm going to let this side have 3A lattice points. Now 3A lattice points means that the length is 3A minus 1. If you think about it, let's say if I have got this square with 3 lattice points on one side, the length is 2. So I need to be very clear when I put that down. It's the lattice points, not the length. Okay, now I'm going to just put a check mark here to remind myself that I have used it. Now, T contains 1/4 of the lattice points contained in R union S. Okay, so I am now going to let T have B lattice points and write down my first equation. So T contains 1/4 of the lattice points means that T contains B squared. So B squared is 1/4 of the lattice points contained in R union S. You have got 4A squared, 9A squared minus the intersection, which is 2A. Now already I can tell that this seems to be quite unlikely, because it isn't automatically going to be a square. Okay, since I see that this clearly means that A is even, so I'm going to just cheat a bit for the purpose of calculations. I'm going to just change this to 4 and 6 immediately. So that I don't have to deal with the fraction. Overlap is 4A, and now this would be equal to 13A squared minus A. Okay, we'll worry about this a bit later because there's still more to come. The fraction of lattice points that in S that are in S intersect T is 27 times the fraction of the lattice points in R that are in R intersect T. I have no idea what that means until I read it 3 more times. But what I think it means is that the fraction of lattice points in S that are in S intersect T. So it says that what fraction of S is this? That fraction is 27 times of what fraction of R is this? Which is a big headache. So what I'm going to do is I just want to figure out what it's saying. Now I'm going to let this be C, lattice points. This would be B minus C plus 1. Maybe I should C plus 1 and B minus C, right? So that it sort of share the burden. B minus C lattice points. Because I am double counting the y-axis when I draw this bracket. So I mean here to here and here to here. Now, I'll keep this equation in mind for later. And I am going to just write down the statement. The fraction of lattice points in S that are in S intersect T is C plus 1 times B over 16A squared is 27 times of B minus C times B over 36A squared. Okay, this turned out to be not that bad, right? It's just a very weird way to tell stuff about A, B, and C. So I cancel B over A squared, simplify the fractions, and you get C plus 1 over 16 equals to 3/4 B minus C. Okay, I think I can solve this. So C plus 1 equals to 12 B minus C. And so 13C plus 1 equals to 12B. Now that's interesting. That's interesting because 13C plus 1 equals to 12B. It just means that because I need to make sure that C can be chosen, it means it can happen. So how do I know that there is such a C? It just means that 12B minus 1 is 0 mod 13. Okay, let me subtract off 13 from 12. So this means B is congruent to negative 1 mod 13. As long as B is congruent to negative 1 mod 13, and of course B must be positive, I'm fine. The question is, what's the minimum possible value of the edge length of R plus the edge length of S plus the edge length of T? It's just mean, right? Because edge length, remember, is not the lattice point. So this is talking about the minimum value of 6A, 4A, and B minus 3. So let's just keep this in mind. This is the thing to be minimized. But as A gets bigger, B gets bigger. So it just means that make A and B as small as possible. I know that I want B to be negative 1 mod 13, and the other equation is that B squared is 13A squared minus A. Now B squared is 13A squared minus A means that if B is negative 1 mod 13, B is 1 mod 13. If B is 1 mod 13, sorry, let me repeat myself. If B squared is 1 mod 13, it means that A is negative 1 mod 13 as well. So I am now going to do a final substitution using these two so that I can find a small solution for A and B. That's all I want. So B equals 13P minus 1, A is 13Q minus 1, and let's just put that in. So I hope this is still comfortably in the screen. It is. So B squared, 169P squared minus 26P plus 1 equals to 13 times of a squared. So is this the best way to do things? I am not sure, to be honest, but I do know a factor of 13 is going to be cancelled out from everything. So let me copy this and carry on the next page. Okay, I will just divide off the 13 straight away and I will see what happens. Minus another q. 1 cancels with this 1, so there's just plus another 1. 26q and q is 27q. And it did not look like this was a very good idea, right? I don't think this is a very good idea. So maybe I should just do something a little bit more primitive, but I think it should work as well, which is that I can look at 13a squared minus a, and I know a and b should not be too big because 10a is in this range. So 10a has to be quite small. Otherwise, it's going to explode. I also know that b is going to be slightly bigger than a. So I think that I can just try the values of a being negative 1 mod 13 because the equation looked too horrible. So let's try a equals to 12. What's this equal to? 1860. No, this is definitely not going to work. So let's try a equals to 25. Now actually that wasn't the best way, right? I could actually have just factorized it like that. Now I'm seeing that since a is 25, this would allow me to see 25 is the square, and then 25 times 13 minus 1 is 324, which is 90 squared. Oh, that's great. So b is 90 and a is 25. So this would give me 340 minus 3, which is 337. Well, this is really mean, right? Because 340 was an option down there, and if anyone, after all this effort, put that down, that's actually quite sad. But there you go. This is the AMC10 from, well, rather the AMC10A from last year. So let me know how you got on. Do feel free to discuss the so-called more proper solutions to some of these problems. And as always, let me know if you have any other comments or suggestions for the next few videos. So thanks everyone for watching, and see you again next time.